Hello everyone and welcome back to Calc 2. We are going to start a brand new unit, which is going to be very different from everything we've done so far this semester. For the rest of this course, we will actually probably do very limited integration. We're going to focus back more on those limits. So if you haven't watched previous review of limits video, please take time to watch that before you get into chapter 10, because limits and finding limits is going to be a big part of what we're going to be doing in this unit, which is all on sequences and series. So before we begin, let's give a little overview of what exactly we mean by a sequence and a series. So a sequence is very simply an ordered list of numbers. Ordered list of numbers. And we order these numbers through n. So what do I mean by that? What do I mean by ordering the numbers through n? So a lot of this right now is going to be all about understanding and learning the notation. So any value, any term in our sequence, we call it a sub n. And we talk about that subscript n, we're really talking about more of a location. So is the set of a sub 1, meaning our first value of the sequence. Now, a sub 2, 3, you get the idea. A sub 4, and these again are all locations. This is for n equaling 1, 2, 3, ... Now, that part that I just put over here is going to be pretty important, because as we go through our sequences and start defining them, you kind of have a choice of how you define n. So, for example, I can show you another one where a sub n be 0, 1, 2, 3, and that would be for n equaling 0, 1, 2, 3, ... Okay, so it's going to be important when you are setting up your sequences or talking about them, defining them, the choice of that starting index, and that's what we call n, we call it our index. That subscript is called an index through n. Let's put that in there. N is an index. It is really arbitrary. It will usually begin with n equaling 0, n equaling 1. It's just you're making things way more complicated if you start with any other value. But it's important that you, number one, pay attention when you're given this information. Is my n value starting at 1 or starting at 0? And define that yourself when you do it. My guess is when you do your math lab problems, you got to look at it to see how they're starting their n. So, of course, these sequences can be generated often with a, you're going to start thinking them as almost a function. And that function as a generator for your sequence in such a way that we'll come up with kind of these equations, or you'll be given these equations for the nth term of your sequence. So, for example, let's suppose a sub n, and I'm going to come up with an f and n. We're going to do a nice simple one, 3n minus 1. Now, this is why I said it's important to know how that n is defined. Is it starting? Is the starting index a 0 or the starting index a 1? So you can't just be given the function a sub n or the formula for your sequence. You also need to be told that in this case, we're going to let n be 0, 1, 2, ... and go on into infinity. Now, some of the things you might be asked to do just to get a general idea, and this is again is mostly taking you through notation is, all right, what does this sequence look like? All right, so here I have my formula for it. This is our formula for my sequence. And this is a nice explicit formula, meaning with this formula, I can come up with any term. If I want the 100th term, I can certainly do that. But let's start by just writing it out. And let's come up with at least the first 4 terms of our sequence. So a sub n would then be equal to, well, you can see I'm starting at 0, so all I'm going to do is plug it in. 3 times 0 is 0. 0 minus 1, of course, is -1. And then you need to plug in 1. 3 times 1 is 3. 3 minus 1 is 2, and so on and so on. Plug in 2. 6 minus 1 is 5. And we can keep going 8, ... But this is considered an explicit formula. So what do I mean by that again? I mean, with that particular formula, I can come up with any term in my series. I can say, hey, what is the 100th term? Oh, well, A, with an index of 100, is just 3 times 100 minus 1. So it's at 299. So explicit formulas are nice because they let you, and we'll see in a minute, there are other types of formulas that are quite so explicit. One other thing as far as notation goes, not a notation I generally use, but you might see in your textbook this particular notation that says, hey, here's a series A sub n, and instead of listing n equals 0, 1, 2, 3, and so on, they kind of put off to the side the beginning. So n will start at, I don't know, 0 and go to infinity, or you might see A sub n is starting at 1 and going to infinity. So that's just a slightly different notation you might come across. And what that notation does is it tells you what your starting index is. All right, so let's take a look at another one. And we don't have to just use n, we can use b sub n. So if I define it as b sub n equals 2 over n squared, where n one, two, three, ... Again, so far you're like, well, there's nothing hard here. All I have to do is plug in my n's and I can get my value. So you can go ahead and do that, and you can see right off the bat, 2 over. Now, if you start at 0, let's take a look at this for a second. We actually have a problem because you can't start this particular one at 0. Why is that? Because if you can't plug in 0. So for this particular, we would start at 1. You just would not pick 0 for that sequence because you can't plug 0 into that particular formula. So we'd have to start at 1, which gives us 2, 1/2. Yeah, because 2 over 2 squared, 4. And when you plug in 3, you get 2/9. And then you get 2/16, which is 1, right? You get 2/16, but you can write that as 1/8, 2/25, and so on and so on. So that's how we would write out our particular sequence there. So this is a good point to kind of go over some basic patterns, because these are going to become quite familiar. The whole rest of this chapter is going to build and build upon these sequences and actually series, which we'll talk about in a little bit. but it's going to build upon them. And recognizing some of these patterns is going to be very useful to you. So obviously, let's say a simple n is just, again, pay attention to the index starting point, but could just be 0, 1, 2, 3. N squared, obviously you should be able to recognize that. And when I say recognize it, meaning if you see this sequence forming, you know, oh wait, that's an n squared, okay? Obviously n cubed is a good one to recognize. And, you know, I think you'll recognize these pretty easily. They're just common patterns. Another popular one is like taking like 2 to the n. So it's kind of good to get a look at what that one is. So if n is 0, 2 to the 0 is 1. Then you have 2, 4, 8, 16, 32, and so on. 3 to the n is another nice pattern. So 3 to the 0, 1, 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th is 81, and so on and so on. Again, some nice patterns to recognize. 2n. These are your even numbers. So it's a way you would represent your even numbers. And then, of course, 2n plus 1. So if you see these numbers listed, your odds, that was supposed to be an 11. 2n plus 1 is a common way to write your odd numbers. Another one are, you know, variations of things like 2 to the n. So 2 to the n plus. I meant, sorry. Yeah, 2 to the n plus 1. Be careful, the plus 1 is not on the n. You know, a little bit harder to recognize. You take 2 to the n, but then you add 1 to it. So we're looking at 2, 3, 5. And if you only go this far, you've got, you know, maybe you're not sure what the pattern is at this point. 9, 17. So 2 to the n plus 1, when you see this pattern of numbers, it is pretty common. 2, 3, 5, 9, 17. Another thing to be careful of is alternating patterns. So how do we take a pattern and alternate it between negative and positive? What if we want to alternate the sum? Well, all you're going to do is take -1 and then raise it to the n power, because n is only going to go up by 1, so it's going to alternate between negative and positive. So can you come up with, say, the general formula for, based on what we just did, let's do 1, -1/2, 1/4, -1/8, 1/16. So what do you think that general formula for this particular sequence would be? First thing I want you to notice is that alternating negative sign. So again, be careful when you do develop that formula, that function, the sequence generator, whatever you want to call it, you do have to define where n is. And it is very often, especially with something like this, to kind of start at n equals 0, especially when you start with 1, because anything to the 0 power is 1. So if n is starting at 0, we can see that, and this would be our a sub 0. Sorry, it moved on me. So this would be my a sub 0 term, a sub 1, a sub 2, a sub 3. So you can see where the taking that -1 to the n is what's going to produce those negative signs on those odd terms. Do you see that? So that's going to be part of it. And then clearly we have a fraction. You look at that denominator. What's that? Well, it's 1, 2, 4, 8, 16. Which of these patterns goes 1, 2, 4, 8, 16? And there it is. It's that 2n pattern again. So -1 to the n over 2n. And there's different ways you can leave it like that. That's certainly acceptable, but to the n, sorry. I said 2 to the n, but I wrote it as 2n. I apologize. -1 to the n, 2 to the n. Notice also, start to kind of simplify your formulas, because they are both, the -1, the 2 are being raised to the n power. So that can simply come down to -1/2 to the n. So a sub n equals -1/2 to the n, where n equals 0, 1, 2, ... So you can have very simple alternating patterns as well. Take a look at this one. So think about for a minute what that's going to look like. How you're going to define it. There are different ways to define it, different ways to come up with the explicit formula for this particular sequence. And that comes down to how are you going to, define your n very often. So play around. Do notice this is not starting. You got to be careful, because we have to use that index, right? And we can, we do a sub 0, a sub 1, a sub 2. We need to use the index within our formula. So notice and think about what your initial value is if we're going to start with n equaling 0, 1, 2, 3, and so on. So we have a -5. So check this out to the n. And see if that makes sense. You need to have -5 in there, or not. This is one way of doing it. Let's check if it works. When n is 0, we actually get -5 for our initial term, so that's good. When n is 1, we get +5. When n is 2, we get -5. So that does work, but that's not necessarily the only way to do it. Suppose we wanted to do it with a +5. And we're letting n start at 0. Then perhaps we need to take n plus 1. So that's another way of writing this particular function. Of course, you can also define it by starting n at 1. As we stated earlier, it is arbitrary how you do that. So there's two different acceptable explicit formulas for that particular sequence. Take a look at one more. Sometimes they're not quite as easy to see. Sorry, I forgot my dots. And you know, there's different things you can try. To get from one term to the next, you can see if there's a common difference. This one's, you know, it's not quite a common difference. So turn it off, hit pause, and just play around with that for a minute. So did you come up with anything yet? Again, this is where these patterns really do come in handy. So what am I? I'm looking at 1, 7, 17, 31. Right? 1, 7, 17, 31. We'll take a look here for a minute. So 7, 17, 31. Well, what happens if I double? I got 8. If I double 1, I get 2. If I double 9, I get 18. I get 32. I get 50. So I got 2, 8, 18, 32. 2, 8, 18, 32, 50. Do you see what's happening? Yeah, it's actually n squared doubled and then subtract 1. So you end up with doubling n squared and subtracting 1. And then that would work. So sometimes you got to kind of play around with the particular patterns to get there. There's all different kinds of ways to get to these formulas. So just in general, we're not going to spend too much time getting into coming up with these patterns, but you can look at differences. What's that? That's 14. That's 18. 59, that's 22. So just as a general rule, if your first set of differences, this is called the first set of differences, if that first set of differences are constants, you have what we call an arithmetic pattern. And we will go through arithmetic sequences in this chapter. But that's not happening here. What we have is our second set of 4. Do you see that? Your second set of differences. Because our second set of differences are constant, we have what it ends up being a quadratic. There is a way to get it using a system of equations. It's actually not bad. I don't know that you'll need it for MATLAB, but just in case. Because your general quadratic looks like this. Hold on. We'll use n squared plus bn plus c, right? That's a general quadratic equation. When n is, say, I don't know, let's use 1, 2, and 3. When n is 1, right, we get a plus b plus c. There's when n equals 1. And that works because we 1, 2 minus 1 is 1, equals 1. That's when n equals 1. When n equals 2, well, then I would get 2 squared, that's 4a, plus 2b plus c equals 7. And when n equals 3, I would get 3 squared, 9a plus 3b plus c equals 17. You could actually solve the system and you'll end up with a equaling 2, b equaling 0, and c equaling -1, and which is what we got just by knowing the common patterns. So there are ways to do it if it's a quadratic. If it's an arithmetic and your first set of differences are common there, that's a much easier one to come up with. But these quadratics get a little bit more complicated. You can solve them using a system of equations. And as you get into, let's see, I would say in linear algebra, you're going to do a lot of that, but you learn how to solve these systems, using matrices and stuff. So if you work this whole system out by grouping the first two, subtracting c, grouping the second two, getting rid of c, getting rid of your a's and b's, you'll end up with, again, a equals 2, b equals 0, c equals -1, because that works. Okay? So lots of ways. They're kind of like puzzles. These are little puzzles that you played, right? You did these in grade school. Here's a sequence. Figure out how you get to the next term. So what we're coming up with here is just a general nth term formula. Now, there are other kinds. There's what we call recurrence relations. You can create your new term based on your previous term. So what we did up here is what I called explicit formulas, because I can use those formulas to come up with any term. I can go, hey, what's the 100th term? I can plug in equals 100 squared, and I can get the term for that particular sequence quite easily. Recurrence relations is when you use the previous term to get the next term. So a sequence may be generated by a recurrence relation when a sub n plus 1 equals some function of the previous term, a sub n. Okay, that's when, again, the next term is developed by some function of the previous term. This is also called an implicit formula. Now, what is more difficult with implicit formulas, you have to know every term prior, or at least the previous term. So if you want like the 100th or the 150th term, if you don't know the 149th term, you can't use the recurrence relation to get that term. But they're still good to play around with. So for example, if I said a sub n plus 1 was equal to 2 times a sub n plus 3. Now, in order to use a recurrence relation, you need to be given that initial value. So we'll set the initial value at 11. If you're not given the initial value, you can't really come up with all of the terms because you have to have a starting point, right? So I know a sub 0 equals 11. So I can do a sub 1. I wrote a sub n. Oh, we'll follow my pattern. It's going to be 2 times. So if my n plus 1 is 1, I have to go to the previous. And that would be 25. A sub 2 would then use the 25. So that's a recurrence relation. You must use the previous value to get the next one. So to get a sub 3, I need 2 times a sub 2. Then I can add my 3, and I get 109, and we'll do one more. And I can say dot, dot, dot. This pattern then equals 11, because that was the starting value, 25, 53, 109, 221. But this is given the recurrence relation. If I wanted, I don't know, the 100th term, I would have to go ahead and find all 99 terms, unless I can come up with my explicit. So our recurrence relation, oops, or what I would call the implicit formula, is an plus 1, what was it again? 2a to the n plus 3. Much more difficult to get the explicit formula on this one. You can play around with it. It is not a quadratic, so you can't find common differences. It's a bit of a mess, actually, to try to do that. But if you do go back to your patterns, it's a little crazy. You know, sometimes the pattern helps you a little bit. If I tried to do differences, I start to see this number 7 come up a lot. So that has something to do with it. And if I go back to those common patterns, and if I look at 2 to the n and actually take 2 to the n and multiply by 7, you start to get numbers near these values. In fact, they're within 3. So you could say, well, let me do this first, because also the other thing I want to point out, if a to the n plus 1 equals 2, a to the n plus 3, another way of writing that is to say a to the n equals 2, a to the n minus 1 plus 3. So your explicit becomes a to the n 7 times 2 to the n minus 3. And you can check that by checking like the 5th term or something along those lines. Now there are other relations that you're very familiar with. Of course, we have the Fibonacci sequence, famous sequence. 1, 1. Remember, you just add the 2 previous terms. 2, 3, 5, 8. 8 and 5 is 13. 13 and 8 is 21, and so on and so on. So, of course, the way to get this one is we can do a equals n plus 2, because we need 2 previous terms, equals a to the n plus a to the n plus 1, where a sub 0 and a sub 1 you have to define them and have to start them at 1. Of course, you can do a sub 1 equals a to the n minus 2 plus a to the n minus 1. You could define it that way as well. The problem is then you can only do this definition for n equaling 2 and n equaling 3 and on, because you need those first 2 terms. So this, of course, is a recurrence formula, and it is so dependent on the previous 2 terms. The question is, well, how do we get the 100th or the 1000th term of the Fibonacci sequence? Was a mathematician, Binet, who did prove an explicit formula for Fibonacci sequence. I'm not going to write it out. It's insane. It's something like, I think it's like, is it 1? It's 1 plus square root of 5 over to 2 to the nth power minus 1 minus square root of 5 over 2 to the nth power divided by square root of 5, something along those lines. And it was proven. So we can get it. It's quite the proof. If you want to see it, you can look up Binet's proof. And that will show you an explicit formula for your Fibonacci sequence. You could literally get other forms. The issue is, of course, with our calculators and working with square root of 5, you're getting estimates. So if you take your calculator and try to find like the third term, you'll get like 1.99 instead of 2. But anyway, so these are your sequences, and these sequences do go on into infinity. So what we want to do is talk about convergence. In other words, what is happening as your sequence grows? This is going to kind of pick up with some of the stuff you learned at the end of chapter 8 with those improper integrals. So for example, we'll do one you're familiar with. Here, very simple sequence. Again, this one, by just how it's defined, you cannot start at n equals 0, of course. So it's going to be 1/2, third, and so on and so on. So you need to look at these as functions. You all know what the function of 1 over x looks like, but these are not functions in that they are just a set of numbers. They're not a continuous function. So when we talk about graphing it, all you're graphing is that set of numbers. You can certainly graph the function 1 over x to see what it's going to look like, but you're technically, because it's a sequence and not a function, you know, at 1 you have 1, at 2 you have 1/2, a third, boom, boom, boom. It's starting here. And of course, I automatically did what I always want to do when I have points, is get it. All right, so this is what your sequence looks like graphed. Again, it is just a set of numbers, and we're working with our natural counting numbers here. You're not plugging in n equals 1/2 or n equals a third. These are just discrete numbers. So your graph is just dots. That's it. But where are those dots headed? So here's the big question. Are they converging? And if they are, what are they converging to? Or, so in this case, yeah, I think everybody clearly can see that a to the n goes to 0. So we say it converges, and it converges to 0. Because if you say your sequence converges, you've got to say what value it's converging to. Where I take another sequence, b to the n equals, oh, keep it simple, 3n plus 1. Of course, what does it look like? You could start at 0 at this one if you want. If you start at 0, you get 1. At 1, you get 4. At 2, you get 7, right? At 3, 9, you get 10, and so on. So this one is clearly 1, 1, 2, 4. You know, it's a linear relationship, so you can see what's happening here. Again, series of dots, not a line. And trust me, the first thing I'm going to do is connect those lines as I did in the last problem, but we're not going to do that. And we would say this one actually diverges. So we say D. That does not look like a D. I don't like that D. So we say it diverges. And when you diverge, you can only diverge to either positive or negative infinity. So it diverges to positive infinity. Often you'll just be asked if it converges or diverges. So how do we test this? So throughout this unit, you are going to learn about these series of tests. And I will post a document for you that'll summarize all the different tests. This is our first test, and it's most of the tests we're going to do are for series, not necessarily sequences, but this particular one is for a sequence. The test for convergence of sequences. So this test is pretty much what we just did in the last example, and it has to do with limit. If you simply take the limit of your sequence as n approaches infinity, then if your limit equals L, meaning it actually equals a value. So if the limit of a to the n as n approaches infinity equals L, then the limit exists and converges to L. If the limit as n goes to infinity of a sub n equals positive or negative infinity, then the sequence diverges. So the sequence converges if the limit has an actual limit. If the limit does not have a limit, it goes off into infinity, then the sequence diverges. Based on that, and based on that limit review we just did in the previous video, if b to the n equals e to the n, and we want to determine if it converges or diverges, we simply take the limit as n approaches infinity of e to the n. We know we can picture a graph of e to the n. That goes to infinity. Therefore, we have a sequence that diverges. All right. If b to the n is a very basic, let's say 3n minus 5, then the limit as n approaches infinity, this is a simple polynomial. It too is going to equal infinity, and it's going to diverge. And from this, some simple kind of laws come up that are very much like our general limit laws, but we have limit laws for sequences. So your limit laws for sequences, let's suppose we have limit as n goes to infinity, a sub n equals a, and let's let the limit as n goes to infinity of b sub n equal b. So here are some simple laws that can help you in solving some of these. If you're adding or subtracting two sequences together, you have to take the limit of the sum or differences of two sequences. It's just going to be their limits added or subtracted together. If you're multiplying a constant by a sequence and you know the limit of that sequence, then it's just that limit times the constant. Again, I think you're familiar with these types of laws. And with limits, you can separate the product and do them separately and just take the limit of a to the n times the limit of b to the n, which means that would just be a times b. And same with division, right? So if you can do the numerator separate from the denominator and you know each of those limits, you can just put them together, okay? So let's look through a couple quick examples. First one, Remember, what we are looking for is whether these limits converge or diverge. If they do converge, you would normally state what they converge to. So example 1, a to the n equals 3n minus 1. That's the limit as n goes to infinity of 3n minus 1. And that one's clearly going to diverge. So what you can do with each of these is just hit pause, try them on your own, and then unpause it and see if you got it right. Example 2. Let's have a to the n equal 3n to the 4th over n to the 4th minus 6. So I'm taking the limit as n goes to infinity, 3n to the 4th over n to the 4th minus 6, which, if you looked at them separately, or if you, not looked at them separately, sorry, you don't want to look at these separately, but if you use the rules we did in the limit review, in the previous video in the limit review, you, at this point, can start to do your shortcuts to say, look, they're both an n to the 4th power, so because they are the same power, I can take their coefficients, and it's just 3. So it converges. So again, this is why I did the previous video with all those limit laws, because it's going to come in handy, as it will in this next one. 3. A to the n is n plus 5 over n to the nth power. So if you recall, this should look very familiar to something that was in the review that I said, please make sure you know this. The limit, I'm going to do the general. If you just learned the general rule, then you don't have to worry about the other one, of 1 plus anything over n raised to any power was e a times b. Because of 1 plus 1 over n raised to the first power is essentially the definition for e to the first power. So if you have any value in the numerator over n and raised to any power b to the n, b to the n, then it ends up being just a times b. So that one's very helpful, but you're like, well, how will I use what I have here in blue on this particular problem? So this is where a little bit of algebra manipulation comes in. So we have to take the limit as n goes to infinity of n plus 5 over n to the nth power. So how can I get it to look like that? Simply break up the fraction on the inside. N over n is 1. So for this particular problem, my a is 5, my b is 1. So it's just e to the 5th, which means it converges. All right. Go through a couple more examples and then we're going to keep going. Number 4. Again, I'm going to go through these kind of quickly. We're just looking for converging and diverging. And it's a great review of limits. How about n to the 1 over n? Well, I just made that one a little bit harder, didn't I? So, limit as n goes to infinity of n over 1 over n. And you're like, well, I know there's something n to the n. This is an infinity to the 0 power. That's not really going to help me right now. So what you need to do with this particular problem, so this one's the tricky one. And we're going to kind of do a little bit of some algebra manipulation here. Because if you try to plug in infinity, you get like infinity to 0 or something like that. It's not going to work. So in the section on L'Hopital, we did some problems where we used the relationship between the natural log and e to get rid of exponents. Natural logs are great ways to get rid of exponents, and that's what we want to do in this particular problem. But I'm going to change it up a little bit. I don't like n to the 1 over n. So I'm going to do essentially a u sub, which, you know, you've worked with u sub with integration. All I'm going to do is sub out and say, well, I'm going to let u equal 1 over n. Well, that means n equals 1 over u. And in doing that, my limit simply becomes, as long as I go back before I'm done and remember I did this, right? It becomes the limit of 1 over u to the u. Now, let's think about this for a minute. N was approaching infinity, but now I flipped that. And if I put 1 over infinity, I get 0. So u is actually approaching 0. So you just get it. That's like changing the boundary in the integral. So we're going to play around with this for a minute. I said this was a tricky one, but I wanted to show it to you in case you come across something like this. And no, I know you're all thinking, you're going to put this on the test. No, I did not put the hardest problems on the test, but that doesn't mean you shouldn't go through them and try them. So I want to use this idea. Well, I can only use the natural log thing on equations, but that's okay. I can make this an equation by saying I'm going to let this limit equal something. It doesn't matter what I let it equal. It could equal L, equal whatever you want it to equal. I'm going to use Y. I'm going to let it equal Y. In doing that, I can go ahead and say I want to take, now I can take the natural log both sides because I have an equation. I'm going to flip it around a little bit and say the natural log of Y equals, I'm going to use a rule that tells me I can move the limit outside. The limit as u goes to 0 of ln 1 over u. And guess what my first step is going to be? So instead of taking 1 over u to the u power, right, which isn't going to help me because I still have, now I've got infinity to 0 instead of 0 raised to infinity. Neither of them make much sense. Can't I get rid of the u? Because I'm working with, again, whole idea of using natural log is to remove exponents and put the u out front. Now I have, well, 0. So what would this give me? This would give me u goes to 0. That would be 0 times, as a u approaches 0, you end up going to infinity because you end up with, yeah, the ln 1 over u as u goes to 0 becomes infinity. Natural log infinity is infinity. Okay. Oh, there we are. Really doesn't help us either. But now I'm closer to my idea of L'Hopital. Remember, to use L'Hopital, I need 0 over 0 or infinity over infinity. Having 0 times infinity gets me that much closer because I can use the reciprocal idea now, right? Limit u goes to 0. I had just reviewed this. I'm going to leave ln of 1 over u up in the numerator and put 1 over u down here. Because now I have infinity over infinity. That tells me I can use L'Hopital. So what does that equal? That's going to equal but before I use L'Hopital, because it's going to be so much better to use L'Hopital, how can I make this problem even easier? Instead of these 1 over u's, I can at this point put my n's back. So what I really have is the limit all I did was remember the fact that 1 over u equals n. So L'Hopital states that it's the limit. The derivative of 1 over ln n is 1 over n over 1, because the derivative, we just took the derivatives, right? Which is, well, that limit we can now work out. The limit is of 1 over n. As n goes to infinity, that goes to 0, so that goes to 0. But watch, what do I have now? I have ln y equals 0. How do I get rid of that? Take each to the e, or, you know, powers of e. Y equals 1. And what was y equal to? Simply the, oh, here it is, the limit, our original function. It's the limit of our original function. So the limit of n go to infinity of n to the 1 over n. So that converges to 1. Okay. Also, don't forget those growth rates that we talked about in the last video. So the limit as n goes to infinity of 2 to the n over n factorial. You got to remember that kind of that sliding chart. And in that sliding chart, the idea is that 2 to the n actually grows at a slower rate than n factorial. So your faster growing function is in the denominator. And if your faster growing function is in the denominator, then it converges to 0. But if your faster growing function is in the numerator, because remember, the fastest growing function is n to the n in this comparison of growth rates. So that one goes to infinity and diverges. All right, so we're going to end with just some basic terminology. We've gone through all the examples, but there is some terminology to understand. And some of it's pretty common sense almost. So sorry about that. Let me write this out. And then we'll be done with sequences. So we covered 2 sections. I know this is a long video, but we did cover 2 sections, 10.1 and 10.2. And in the next video, we're going to get into series, which is really just adding the terms of your sequence. First one, a to the n is an increasing sequence if one value that is further along is greater than the value before it. Makes sense, right? N plus 1 is greater than a to the n. Now, this is where it gets tricky. The word non-decreasing, which is different than increasing, by the way. Okay. If a to the n plus 1 is greater than or equal to a to the n. All right. Non-decreasing. This is because you can literally have, like, an example would be, we'll give an example, 1, 1, 2, 2, 3. Okay, we're increasing will be 1, 2, 3. Okay. So non-decreasing means, well, you could have terms. It is not an, well, yeah. Okay, it is also increasing. Keep that in mind because the a to the n plus 1 is also greater than a to the n is part of the definition. A non-decreasing function is always also an increasing function, but an increasing function is not necessarily a non-decreasing function. Just ponder that for a minute. As we do the same definitions for actually decreasing. Of course, if a to the n plus 1 is less than a to the n, and then you got it, non-increasing if a to the n plus 1 is less than or equal to a to the n. So a decreasing function is always non-increasing, but a non-increasing function is not always decreasing. Again, just think over that one. Monotonic. So here you go. A to the n is monotonic if it is either non-increasing or non-decreasing. It has to move in one direction or the other. Doesn't matter how it moves there, but it has to move in one direction or the other. Okay? As long as it moves in one direction or the other, it is. Monotonic. And when we see some stuff with our series, you'll see stuff that is not necessarily monotonic. All right, a to the n is bounded above if there is a number I'm going to call it m such that a to the n is less than or equal to m. That means every single value that sequence is under a certain value, then it is bounded. It is bounded below. And all of these, I believe, are written out in the PowerPoint notes. If you don't like my writing, you can grab them from there and just, they're summarized in there. If there's a number n, we'll call this one n, such that a to the n is always bigger than n. Now, so I know you're asking, what if it's bounded above and below? So if a to the n bounded above and below, then it's just called a bounded sequence. Can you think of a bounded sequence? Not a bounded function, but we can turn any function into a sequence, right? We're just using the whole numbers, 1, 2, 3, 4, 5, 6, and we're not using all the stuff in between. What about tan inverse? What about that? Our tan inverse is our tan graph on the side. Okay, it's got this asymptote here, because remember this is the inverse function, so we flipped it on the side. And the tan function is gonna okay, it's a function, but it's not a function because it's a sequence. So notice I got to use the dots. Again, like I said, I want to connect these dots so bad, but I cannot. Right? We just have them at the whole numbers and the negative. It's fine. So, well, actually, we just have them at the whole numbers. 1, 2, 3, 4, and so on and so on and so on. Yeah, that's a bounded, right? It's bounded above and below. There's values it cannot go between. So, and we have a theorem that says that any bounded monotonic sequence converges. They won't diverge, they will converge. All right, so that's, again, just some, I did it, hour and 6 minutes. I was trying to get under an hour. That's your 10-1, 10-2. Go through the homework problems and what you can do.